So the first thing that we're going to do is we're going to be digitizing our signal. What does this mean? It means converting from the continuously varying pressure of the sound wave. These particles are moving together and apart from each other and in the vicinity of the microphone, and we record that pressure through the medium of voltage. But the computer it can only record discrete values. What does that mean? It means at a particular moment, it can record a number that represents the amplitude then. And then it waits to the next moment it's ready to record, and it records another number. And it records a series of numbers representing amplitudes. It can't record every moment because there's an infinite number of moments and it doesn't have an infinite number of space, and an infinite amount of space. And equally, it can't record infinitely precise measurements of amplitude because an infinitely precise measurement takes an infinite amount of space, and we don't have that. So it's digitized, it's made discrete. So we take a finite number of evenly spaced measurements in time, and each of those measurements has a way of representing amplitude that breaks the amplitude space up into evenly spaced intervals. So how is this going to work? There's some things that we need to look out for. So first, let's work in the frequency domain. We'll be paying attention to the frequency domain to begin with. Here is a wave. This is a nice smooth wave, and the computer comes along and it starts maybe right at the beginning here, and it takes some samples. So there's some dots representing the samples that it takes, evenly spaced in time. Of course, the computer only sees those dots. It doesn't see the wave. It only knows what it's measured, what it's recorded. And so you could imagine connecting these dots with lines. And what we have here, if we go back to our original wave, that original wave had 4 full cycles. And what we have here is, it's basically 4 full cycles. They're shaped a little bit differently because the computer doesn't have all of the detail, but there's our 4 full cycles. And that's with 17 samples across those 4 cycles. But when we set out to record, we don't know how frequently the wave is varying, so our samples aren't likely to line up as much. So here's also equally spaced in time, a set of samples, and this is actually 10 samples across that same wave. And if we get the computer to reconstruct it, we get 1, 2, 3, 4. We do kind of still have 4 peaks. So it's still somewhat like our original wave. We see the amplitude is doing some funny stuff because things aren't lining up with the peaks as nicely. And now what if we have only 7 samples? With those 7 samples, the reconstructed wave has at most 1, 2, 3 peaks for our 4 cycle original wave. So it's representing about 2.5 cycles here with 7 samples. Here's another set that happens to be lined up nicely. This is 8 samples, and we get 1, 2, 3, 4 peaks, more or less here. What is this telling us? Basically, there's this principle, the Nyquist principle, that if you want to be able to capture a particular frequency in your digital representation, you have to have at least 2 samples per cycle of that frequency. Or in other words, you have to sample twice as frequently as the wave is cycling. So the sampling frequency has to be twice the frequency of the wave that you're interested in. Okay, and there's some other stuff that comes along with that that's discussed in the textbook about filtering a wave, the analog wave, before it even hits the digital realm, filtering it so that any higher frequency elements are gone before you digitize it. Because as we saw, if there's a high frequency wave and our samples aren't up to capturing it, it's going to give us something. It's going to give us a lower frequency wave and say, hey, this is what I saw, more or less. So it's going to be introducing things that aren't there in the original signal. So you got to filter that stuff out first. The main thing to remember for now from here is that Nyquist principle, that you've got a sample at twice the frequency of the highest frequency wave that you want to be able to represent with your digital signal. Uh, so that's digitizing in time, and that can be represented here. Here is a much finer gradation of vertical lines. We also digitize the amplitude, uh, and I'll talk about that a bit more in a second here, to give us this sort of grid of fine little boxes that represent the actual resolution of our sampling domain. So what about that amplitude domain? Well, each sample is a string. It's a number that's given a certain amount of space, and we're working with computers here, so it's binary. So a certain number of ones and zeros, and for every digit, you can represent every digit you add, you can represent twice as many values. So for one digit, you can represent two. For two digits, you can represent four. Three digits, eight, and so on. And what we normally find is that in typical sound recordings for human hearing, 16 bits, 16 binary digits is pretty good, and that gives us 65,536 different values that can be represented, from the lowest pressure to the highest pressure that can be represented with one of those samples. And one thing we can ask about that is what's the range of different loudnesses that we can represent? You know, if we had a wave that was just going sort of one bit up and down and up and down, that would be sort of the quietest wave that isn't silence that we could represent. And then a wave that's going from the highest value to the lowest value and back and forth, that would be the loudest, the highest amplitude sound that we could represent. So what's the range there? And we actually already have the math for that. We can use our logarithm calculations and compare, you know, a waveform that just varies by one unit in this digitized realm to a waveform that varies by all the units. And when we do this calculation, that's about 96.3 decibels, which means that the difference between the quietest sound and the loudest sound we can represent with 16 bits of amplitude resolution is a range of 96 decibels or so. Okay, so so a 16-bit resolution can represent that, and in speech, we're often interested in the first 5 to 10,000 uh, hertz of frequency. So our recordings will be from 10,000, we need to record at least 20,000, and often we'll double that just to be on the safe side. 10,000 is pretty good for speech, but there's other sounds that we can hear, so we'll often record at, and I realize it's not a round number, 44 to 48,000 hertz, 44 to 48 kilohertz as a frequency, a sampling range that we use. So the full path here, we have our original analog signal. It gets filtered to remove those high frequencies that are going to introduce some garbage. We digitize it, restore it, process it in the computer, and then there's the reverse process, reconstruction from the digital to analog. That we don't have to worry about the engineering details here, but know that that is something that happens when we're playing a sound back out of our computer. And sounds can end up being very large files compared to text, for example, small compared to video, large compared to text. And one thing that is often done is that they're compressed. There's ways to sort of throw away some of the information there that isn't buying us much in terms of what we hear, and so they get compressed. So, for example, an MP3 file, which is how a lot of music is stored, it's crafted so that the information that's thrown away is the stuff that our brains wouldn't notice anyway, and you can get much smaller files, like a tenth the size of a file that lists each of those samples one after the other. That's literally how a basic sound file could be represented, but there's ways to reduce that file size. One thing about compression is that if you compress and then you do some editing and then you recompress, you throw away a bit more information each time and you get a degradation of the signal. That's kind of beyond our scope here, but it is worth knowing. Anyway, so that's basically it about digitizing in the time domain and the amplitude domain. Next up, we're going to look at different types of waves.